Let's look at heats of reactions. Many times we'll do a chemical reaction simply to obtain the heat that they give off. This is especially true, as you might imagine, with combustion reactions. For a reaction, we can figure out the enthalpy change, the heat change, from subtracting the heat of the reactants from the heat of the products. We call that delta. Delta means difference. Consider the exothermic, that means heat coming out, reaction of the combustion of hydrogen with oxygen to make water. This gives us a heat outlay or emission giving off. The negative sign tells me that I am emitting heat. Okay? And this is kilojoules. This is 1,000 joules. Remember, joule is so small, we have to use 1,000 joules. But we call this a thermochemical reaction, thermo meaning heat, because it always refers to the moles of reactants and products, and the heat energy associated with the reaction is written. Therefore, if I had twice as many moles, for example, if I had 2, 1, and 2 here, I would have 2 times as much heat. That should make sense to you. If I have double the quantity of fuel, I should get double the quantity of heat coming off of that. Let's look at some practical problems because these are extremely useful, and we're going to intertwine our discussion of stoichiometry, that is, relating the number of moles in a reaction to each other. All right? I could read this reaction simply as, and she is octane, which you might have heard of. Octane comes from the 8. Okay, if I react 2 moles of octane with 25 moles of oxygen, oxygen gas is a diatomic. He is 2 oxygen atoms bound together. I will produce 16 moles of CO2 and 18 moles of H2O. Naturally, I could do this on a molecular level using simple molecules of each of these, but we don't use those kind of quantities in real life, so what's the point? So we are talking about moles. Moles are approximately 10 to the 23rd. That's 10 with 23 zeros after it, molecules. Okay? All right. And the amount of heat I would get off is pretty impressive at about 11,000 kilojoules. And remember, that means it's given off. So I can figure out how much heat I produce if I burn 4 moles of octane, and that is using this thermochemical equation as a conversion factor. For example, I know that if I burn 2 moles of the octane, I will produce, and I'm going to keep using the same negative sign so I keep track of that. That's much heat is produced. I'll use this as a conversion factor by dividing, making this an equal sign. Remember that it's equivalent to, so we can write that as an equal sign, and dividing both sides by 2 moles. So this tells me that I get 10,992 kilojoules for every 2 moles of octane. Well, what if I, like I say, I don't, oh, that's 18, I'm sorry. If I don't have 2 moles of octane, no problem. I say I have 4 moles. I don't know why I insist on doing a 16 there, but I'll keep fixing it. All right, now I use my conversion factor. 2 moles. I know that 2 moles of the same stuff will produce this much heat. So I simply do the math, and I find I've got, well, you can see here I've got twice as many moles of the octane. So, would I expect to get twice as many moles of the heat? You betcha. So it'd be approximately 2 times 10,000, or let's just say approximately 22,000 kilojoules. I'm simply multiplying 2 times negative 10,992 kilojoules. I'm a great believer in estimating. Number one, it gets the math out of the way as a hindrance to understanding. And number two, it's faster. Okay. All right. So that's one problem. How about another one? How much heat is produced with the combustion of 50 grams of, of octane? Well, in this case, we have to figure out one, how many moles is 50 grams of this specific material, and then use the conversion factor, or in the thermochemical equation to determine heat for this specific amount. Good enough. And a variation of this is done actually by the people who supply the methane natural gas to the homes in Columbus. They will figure out how much methane they have to buy for one of our winters in order to give people as much heat as they want. So how do I figure out how many moles is 50 grams? I have to figure out the molar mass of my molecule. And that simply equals the sum of the atomic masses, right? So written out, that it would be 8 times the atomic mass of carbon plus 18 times the atomic mass, or atomic weight, sometimes you'll see it written as, of hydrogen. And this is equal to 8 times 12.01 grams per mole for carbon, plus, we can put parentheses around just to show which operations we're going to do first. But to tell you the truth, multiplication always takes priority over addition. You always do multiplication, division before you do adding or subtracting. And here's my little hydrogen. And the total comes out to be 114 times 2, 6. And I've gone to the hundredths place, so I'm going to go to the hundredths place here. That is the correct number of significant figures for this calculation. So this is for my whole molecule. Okay, now let's go on to figure out how many moles this is. How many moles? It is 50 grams. And again, you get the hang of this. We're going to divide it by, and remember the MOL is the shorthand for mole, and I'm going to use the reciprocal of, that means the upside down, of my molar mass of C8H18, and I've got 18 grams of that stuff. And of course we can always do that, which I find very exciting, being able to, I'm going to put a mole there, cancel. It's kind of like cleaning house. And I will find that I have, 0.4376 moles of CH. And how come I don't have 23 numbers here? Well, I actually should only have 3, because I only have 3 in my least precise data value. And then, so this is all number 1, and then number 2 is simple. I take the number of moles and we round up. Let's round up to this, to the correct number of significant figures. And then we use the conversion factor from our balanced thermodynamic equation, which says for that much heat, I need to supply 2 moles. Well, I don't have 2 moles, so I think I'm sure I'm not going to get as much heat out as 10,000 kilojoules, and I would be right. And you want to give it a shot? Try to estimate how much? Well, this is about a half a mole. So if I get divide about 11,000 by 2, we say 5.5, and then half again of that, we get about 2,500. You would be right. 24 kilojoules of heat. And again, the negative sign is it's emitted, given off. For combustion, that's the reaction, remember reaction with oxygen, of half a mole, about a half a mole of octane. Excellent. One last one this is about. How many moles of CO2 were produced if I knew how much heat was given off? All right, you ready for that? See if you can, if I give off 2,500 kilojoules of heat, and I know I give off, I can make that one -2, kiddo, because he is emitted, and then 992 kilojoules per, now this is CO2, so I need to look at the number for him, and I have this value of CO2 I just multiply this together, 2,500 times 16 divided by 10,992, and I get 3.6. And how many significant figures should I use? Well, these are considered exact, these values here. So they are not going to impede our or reduce the number of significant figures. So I have to look for this number. And so he's got zeros there. Oh my gosh. Shall we just assume that I have 2 since he's not in scientific notation? I'm just going to assume that these are the only significant ones. It may well be that this one or this one is. I might have 3 or 4, but I'm just going to assume, without any additional information, that there are 2. So I've got 3.6 or 2 significant figures. I'll just write SF for significant figures. Moles of CO2. Good enough. How else can we figure out how much heat is given off? What if we knew how much energy is, potential energy is in each one of these little bonds? Then we could add those up in the products and subtract the amount of energy it would take to break those in the reactants, and we'd have a net heat amount. And that's just what we do. Let's look at ethanol. We're going to combust this stuff. This is the same stuff you drink for as an intoxicant, but right now let's look at it as simply a fuel. And fuel it is. We're using quite a bit of ethanol now as a substitute for gasoline. Let's balance it. Lovely. And there's the reaction written out explicitly, showing all the bonds. Okay. So now we have a alcohol over here, and alcohol is shown. An alcohol by definition has that OH bond. Here's my O2. Okay. Here is carbon dioxide. Notice he's got two double bonds. And here's water. The reason why she's bent is something we'll get to later on, but it's kind of interesting. There gives it a huge number of unique properties because he is bent. Okay. Now, if I look at all the bonds, and I don't want to write it all, so that's why I gave this to you in your chart, but each bond has an energy associated with it. For example, the carbon-hydrogen bond, it would take 416 kilojoules per mole to break that. And conversely, how about over here? Let's come over here for our products. All right, I get a 803 kilojoules per mole emitted, given off every time I form. That is, make one of those. And I have two. Notice I've got one, two of these bonds for every unit of CO2. Every mole, every molecule. And also I've got one, two of these OH covalent bonds. And every time one of those bad boys forms, I get 467. So how does this work out? Well, I'll tell you. I get heat as a product. So the sum of these is going to be greater than the sum of those. That's just a hint. All right, here's our moles. How come I got 5? Count them up. 1, 2, 3, 4, 5. Fantastic. And how come I got 3? Because I've got a 3 out here. So I've taken into consideration the coefficient and the internal number. Why does that become important? Because it can get kind of interesting. Look at the products. I have 4 because I have 2 moles and 2 of the same kind of bond. So that's 2 times 2. And look at the water. I have 3 is my coefficient, and I've got 2 of these same bonds in there. Total them up. Ooh, what's that? Well, I put a negative sign because heat is a product. Heat is emitted. Right? Very nice. Okay, this is how much must be absorbed to break these bonds. You always add heat to break them. You always give off heat when you form them. Great. Okay. Now we can tally it up, the whole thing, and like I said, we will have a 4733 for the reactants, 6014 kilojoules from the products. We subtract the products from the reactants, and we get, watch your signs, a total of 1281 kilojoules coming out of this reaction. It is exothermic. This is why we do this reaction, and we use ethanol for fuel. Okay. All right. We can break down glucose the same way. Glucose, I need you to know that reaction. That's the combustion of glucose. That's what metabolism is. Count them up again. Here they are. I've given these to you. What I'm trying to get to is that this one is giving us this much heat in our little bodies. And this is the fun one. I just want you to look at this. All right, we start off with 4 moles of what's nitroglycerin, which you could shake and blow yourself up, or you can put it with ceramics and make dynamite. This is what made Nobel all of his money. The thing of it is that all the products are very stable. They have very large bonding energies, and this one has got very small bonding energies, so the difference is going to be pretty impressive. That's what makes it an effective explosive. Reactants with weak chemical bonds forming products with strong chemical bonds. So it takes a little bit of energy to break them, and a lot's given off when they're formed. And look at this. Oh my gosh, can you imagine doing this? All these calculations? I won't make you do all that. But just so you can see, and this isn't really that difficult, you just have to be pretty systematic about the whole thing. And it comes out to be minus 5737, very exothermic, really big boom. Right. Now what gets these things started though? Luckily most of these combustion products need a activation energy to get them started. This is the match, the spark, the thing that gets them moving, gets the molecules of the reactants moving with enough energy. Or heat energy, if you will, to get over this hump. And once they do, though, the reaction proceeds spontaneously. This energy between here and here, okay, remember our energy is going up. They say pictures are worth 1,000 words. So path of the reaction. I start off with reactants, end up with products. That's called the path of the reaction. All these interesting terms. But here's the activation energy. This is the thing that gets it started. So reactions don't often spontaneously occur without a little bit of help to initiate the reaction. And the net reaction, though, is the big heat we see coming off. Delta H for this, as written, would have a negative sign. That is, it is exothermic heat given off. Okay.